So I'll be talking about probabilistic solutions to ordinary differential equations as nonlinear Bayesian filtering and smoothing, with a particular focus on Gaussian approximations. And so this has come to be joint work with Simo Serke and Filip. And so here's a rough outline. First I'll introduce the generic problem of numerically solving ordinary differential equations. And then I'll talk a bit about a statistical problem formulation for this problem, and then for approximate Gaussian inference algorithms for solving the statistical problem with some connections to interpolation in reproducing kernel Hilbert spaces. And then I'll say a few words on convergence and then give some numerical examples. And so, ordinary differential equations. So we have some time interval from 0 to t, and then we have some initial condition y0 and a vector field f. And this of course defines the differential equation given in equation 1, so we have the derivative of the solution is equal to the vector field evaluated at the solution, and with the correct initial condition. And so given a discrete mesh, which is a subset of this time interval, we want to find a differentiable function y hat that approximately solves this differential equation essentially. And the way to statistically formulate this problem, more specifically in the Bayesian framework, is to first define a prior process and then some data. And so our prior is going to be this big y of t here, and it's generated by this right hand side here. So this first bit essentially corresponds to the initial condition of y and some of its derivatives, and this integral here is just a Green's function acting on a VNet process. And this Green's function is a differential operator of order nu plus 1, which means that y is nu times differentiable. And by construction, if we stack the nu first derivatives of y into a vector x, then it actually has just a stochastic differential equation formulation. And these EMs are just such that if I transpose it and multiply by x, then I get the mth derivative of y. And so we can compute transition densities, and so we get that are Gaussian with some transition matrix A of h and some process covariance Q of h, where h is the step size or time difference. And these parameters are given by these expressions down here, and so A is just a matrix exponential of the drift matrix, and Q is just the Green's function associated with x interproducted with itself and then integrated over the time interval, and it's defined like this, where theta is a Heaviside function. And so now for the data, well, we can define an information operator, as Cocaine et al. Calls it, which I denote here by Z, which is equal to a differential operator minus the Nemitsky operator associated with f. And so the Nemitsky operator associated with f is just a fancy way of saying composition with f, so it acts on y by putting y inside f. And so then our data of course becomes our information operator evaluated at the prior equals 0 on our mesh, and then we also of course have to condition on the initial condition as well. And this is a good idea if you note that if you put in the solution to our ODE into Z, then we get the 0 function. And for a state space representation, we can write this information operator just as a nonlinear function, since x contains the derivative of y, which I denote by x superscript 1 here. And so now to inferring things from this sort of problem, well, one thing to note is that the map problem kind of looks like this. And so this is just the density of the x process constrained to the grid, and then we minimize this subject to, well, the initial values being correct and the information operator evaluating to 0 on the mesh. And so this is instructive because most of the methods we're going to talk about, indeed all, are going to be solving the map problem exactly for particular vector fields at least. And the sort of template for all the approximate inference schemes is the exact inference scheme for when the vector field is affine, in which case the system is Gaussian and we can solve it exactly by Kalman filtering and smoothing. And so what happens then is we track first some mean vector μf and some covariance matrix sigma forwards in time, and so they solve these differential equations between the grid points, and in discrete time we can of course just write it as product with the discrete time transition matrix and some extra stuff for the covariance. And so this minus here simply means that we haven't updated at Tn yet. And so for the update we compute the measurement matrix C, and you see here the Jacobian of the vector field enters in there, and then we compute the marginal measurement variance and then the Kalman gain. Then we do a correction to the filter mean and covariance. And so this gives us the posterior conditioning on all the data up to the present time point, but if we want to condition on all the data, then we also have to run the smoother step backwards. And so the smoothing mean and covariance μs and sigmas respectively follow these kind of differential equations, and they're supposed to be initialized at the initialized at the terminal conditions at the filtering mean and filtering covariance respectively. And of course we can also solve this on the grid like this, so then we just compute the smoothing gain G, and then we make corrections to the filter mean and covariances like this, so we recurse from the terminal endpoint back to the region. And so all the approximate schemes we're going to talk about can be kind of classified by examining the local map problem. So here we just have the prediction density essentially under the Gaussian assumption, and we want to minimize this subject to the information operator evaluating to 0. And so we get, similarly to classical numerical analysis, 3 kind of different classes of solvers. So a solver is explicit if it solves this problem exactly for constant vector fields in Y, and it's semi-implicit if it solves this problem exactly for affine vector fields in Y, where there's a Y missing there, and it's implicit if it solves this local map problem exactly. And so yeah, what we're going to do is of course make affine approximations of the vector field. So we denote these parameters by lambda hat and zeta hat, and these sorts of approximations can be obtained by, for instance, 0th order Taylor series expansions of the vector field around the predictive mean, in which case the lambda becomes 0 and zeta just becomes the vector field evaluated at the predictive mean. And so one can kind of immediately see that this is an explicit method because the 0th order Taylor series expansion in Y is exact for constant vector fields. And then we have the semi-implicit method, which does a 1st order Taylor series expansion. So we actually get lambda equals to Jacobian evaluated at the predictive mean. And then zeta is the rest of the terms in this 1st order expansion essentially. And we can of course iteratively recompute these parameters and run the update again. And if we do this to convergence, we get the iterated extended Kalman filter, which looks like this. And this one is implicit because it's essentially just a Gauss-Newton method for solving this local map problem. Another class is to consider iteratively relinearizing around the smoothing mean. So we kind of just initialize by running any of the previous methods plus the smoother, and then we relinearize around the smoothing mean, and then we run linear filter and smoother again iteratively until we converge to something. And this is just called the iterated extended Kalman smoother, which again is just a Gauss-Newton method for the sort of global map problem. And it's kind of just a clever implementation of the method from John et al. If you have a state space prior. Now, so the reproducing kernel Hilbert space of Y can be sort of shown easily from results from, for example, Van der Waart and Santen, to be this space. So the M first derivatives, or the new first derivatives of Y, are absolutely continuous, and the new plus first derivative of Y is in L2. And we have this inner product in a reproducing kernel Hilbert space. And so the first bit is just the inner product associated with the RKHS of the initial values, and the second one here, it's just mapping our value back to the RKHS of the Wiener process, essentially, via this differential operator that I mentioned earlier in the definition of the prior. And the kernel is, of course, just given by this expression here. And so, essentially, the class of priors that we're looking at here are not very different from the new times integrated Wiener process. And we know that this is equivalent in RKHS to a Sobolev space of orders nu plus 1. And so it's the same here. And yeah, and we of course have a bunch of representatives for differential operators, so that I denote by eta SMV, which is essentially the representative of scalar product of the mth derivative evaluated at S with V, written like that. And since there is a one-to-one correspondence between the Y process and the X process, the X RKHS is essentially the same, or well, it is the same as the RKHS of Y. So the first subvector in X just needs to be in the RKHS, and the rest of the subvectors just need to be the derivatives of X naught. And so it basically inherits the inner product from Y and so on. And we have this kernel here instead, this P. And so these kernels are of course just the covariance matrices, covariance functions associated with X and Y processes. And so now we can consider this sort of interpolation problem in our RKHS instead. So we want to minimize the norm of our solution subject to it being in a feasible set, and here the feasible set is of course satisfies the initial conditions and the information operator evaluates the zero on the mesh. And we can sort of reduce the search space a bit. So if we define the closed linear subspaces of the RKHS as this Rn of M, which is just the space spanned by the representers of evaluation of the derivatives up to order M at the grid points, then we can see that optimal interpolant is just an element of Rn of 1. So we can expand it in representatives of function evaluations and the derivative evaluations, or the representatives associated with those. But that's not what I'm going to do. I'm going to expand it into the larger space Rn nu instead, and the reason for that is fairly simple. We get the expansion of our optimal point like this, and then we get the RKH norm of Y is of course equal to X, which is just this fat X transpose P inverse X, and this fat P is just a the sort of kernel matrix associated with function evaluations of x, and we know that it's also the covariance matrix, and we also know that it's a Gauss-Markov process, so the inverse is sparse, and we can in fact just write a interpolation problem like this, which just happens to be the map problem. So the optimal interpolant and the map problem are the same. And so that's useful, because then we can talk about whether the map converges. We know it's an element of the Sobolev space nu+1, and so we can use a bunch of tricks from those scattered data approximation theories to establish this. So for any element in our RKHS that satisfies the initial condition, we can simply write it like this. So it looks like the solution to the integral formulation of the ordinary differential equation plus some error term e of y over t. And this e, of course, is just defined as the integral of the derivative minus the vector field, which is just the integrated information operator. And so essentially we can see that our map estimate will converge if we can get this zy to be small enough for sufficiently dense grids, essentially. And so we're going to do this under the standing assumption that f is of smoothness nu+1, and this essentially implies that our exact solution y star is a member of our RKHS, though it also implies a bunch of properties on the information operator that we need as well. And so it's useful to find this field distance, which is the biggest ball in our interval that doesn't contain any grid points, essentially, and it's just half the maximum step size as well. And so before we look into convergence, we might want to examine how this information operator behaves, and essentially a straightforward consequence of theorems 3.1 and 4.5 of Valent from 2013 gives this kind of corollary thing here. And so if we have some open subset of our Sobolev nu+1 space, such that all of those elements take values in some open space in Euclidean space, then the ith coordinate of the information operator is a continuously differentiable mapping from this open set in the Sobolev space onto a Sobolev space of one less smoothness for each coordinate. And if in addition this open set in Euclidean space is convex and bounded, then the information operator is locally Lipschitz as well, is essentially what this is saying. And yeah, so then we can of course combine this with these sort of Sobolev semi-norm inequalities from, say, Arcangeli et al. From 2007. And so essentially if we pick some rho in our RKHS such that it is larger in norm than our solution, and then we can let some q be any number between 1 and infinity, then there are a bunch of positive constants such that for any y in the open set defined by in the ball defined by with radius defined by the norm of rho, the following estimates hold for all sufficiently small field distances. And so here we've just traded the semi-norm of smoothness nu with the norm of smoothness nu, which is and then apply that Lipschitz result. So then we get this. And now we're basically almost done, because for the map estimate it's by definition 0 here. This time it's going to be 0, which is just the maximum value on the mesh. And then we can do things to this term. And then we essentially get this theorem. So for any q between 1 and infinity, there is a constant such that for all sufficiently small field distances, we have the following semi-norm bounds on this error operator here. So this is just the LQ norm of EI, and so we see if we, for instance, put Q equals to infinity, then we converge uniformly at the rate of delta to the power of nu. And then we have some slightly worse convergence rates for the derivatives. Yeah, and so that's nice, things converge. And now we can look a bit at numerical examples. And so I have all two test equations here, the logistic equation with some parameters and initial conditions, and the Riccati equation with some parameters and initial conditions. I probably should have written what C was, but I didn't. And so we can compute the L infinity error for the zeroth and first derivatives, and sort of compare with the predicted rates for the map estimate, which is delta to the power of nu and delta to the power of nu minus a half. And for the logistic equation, it kind of looks like this for our methods. So the green one is the iterated extended Kalman smoother, which should be the map estimators, provided that it converges to the global optima. And this EKS1 is just the first order Taylor method, and EKS0 is the zeroth order. I'm not plotting the iterated extended Kalman filter because it should be somewhere between IEKS and EKS1. But we at least see that our convergence rate for the IEKS seems to be correct, but it kind of also seems to hold for all of the other methods as well, though there might be some offsets for particularly the zeroth order method. And yeah, so that this was actually the solution error, and then we can look at the derivative error, which is essentially the same story. And the black line is of course the predicted rate. And here is an example of the output. So we plot the EKS0 and EKS1 against the ground truth for the logistic with confidence intervals. And so we see here's the solution. The EKS1 looks quite good. EKS0 looks a bit worse, but fairly good as well. And here for the derivative. And so since we're doing linear interpolation here, we can see that we used a once integrated Wiener processor prior, or a once differentiable process at least. And then, yeah, so here we again have the solution errors for the Riccati equation. The story is pretty much the same. We converge at least at the expected rate, but for the map estimate, but all the other methods kind of seem to also do that. So, and the same is true for the derivative. And here again are some cool plots of solution generated by these algorithms with confidence intervals. And so here we're using a more smooth prior since we're not doing linear interpolation for the derivative anymore. Yeah, and so with that I'm done. Here are some references that are key. I guess if you're interested in the convergence stuff, then Arkangeli and Valent are probably the most important ones. Thank you for your attention, and I look forward to your questions if you have any.